Hi, I'm Chun Lin from .NET Foundation. Have you ever deployed your Postgre database and other cloud services to the public cloud service? So sometimes you may have this question. Can I actually performance testing our infrastructure before we actually deploy it on the cloud? Well, today in my talk, I'm going to show you how we can use discrete event simulation to do the shift left performance testing on our infrastructure before we even deploy it on the cloud. So let's start with seeing how we can use discrete event simulation to model our Postgres database performance degradation on Burstable Cloud Instances. Before we start, let me explain a bit about Burstable Instances. So you all know about cloud compute, right? So the general use of the cloud compute is that you have the 100% of CPU credits that you are able to use. However, in Burstable Instance, there's this thing called the baseline CPU. So when your usage is below the baseline, you are able to accumulate your CPU credits. Because of this, when you need more and excess CPU credits, for example, during Christmas or during New Year, you expect more volume to join in to retrieve data from the database. At that time, you will expect a burst in your CPU. So those saved CPU credit can be applied at that time. So this is the selling point of burstable instances. And because you are having a baseline, you actually get 20 to 60% cheaper than the fixed performance instance. So it's perfect for variable workloads, right? Because on the normal days, you don't need so much CPU credits and you can save them and apply them when you need. It sounds good. So actually, how does it work? So if you are working with API uh, limit, you will know this thing called token bucket algorithm. Okay, so let me show you what it looks like in a graph. So you start with some credits available in your instance. Then you run your workload. So when it hits 0, then your CPU will be throttled. So at that time, you don't have excess CPU credits. So you will run your workload at the baseline. And at this time, the server will slowly recovering your CPU credits because you actually only use up the baseline and you earn a bit of the CPU credit. So what is being left over will be your net credit gain. So over time, over some time, your CPU credit will be above the CPU baseline. So when the Christmas or New Year come and it hits the burst mode, that's when you can use 100% of your CPU and you can run a lot faster instead of being throttled. And at that time, those CPU credit being saved will be used up until you hit the 0 CPU credit. Then you go repeat again. So this is the so-called the token bucket algorithm. So in short, you earn credits continuously over time, whether you are being throttled or you are bursting your CPU. And you burn credits when you are using CPU above the baseline. And when there are excessive credits available in your savings, you are able to burst to 100% CPU. And when depleted, you are being throttled to the baseline. So for example, on Azure B2MS, your base CPU performance for that is 30%, and you earn 36 credits per hour and burns 2 credits per minute at burst. So these parameter, these values are very important later when we use discrete event simulation to model our infrastructure. So how do you get this kind of values and parameters? Well, there's a documentation on Microsoft Learn having listed all the Azure B-series V1 CPU parameters. So as you can see, for example, the B2MS that we will be using in our subsequent demo, it has 30% of base CPU performance and initial credit is 60. And it will bank in CPU credit per hour at 36. So when your CPU is throttled, and so you will be using less than 36, then the excessive amount will be saved. And how much you can save? Well, of course, it based on the size of your instance. If it's B2MS, you will be at the maximum of 800 x64. So if you would like to know more about this table, you can take out your phone, scan the QR code over here, and you can find out more about this information. Okay, so what's the problem of this? It sounds good, right? I don't need so much CPU when it's not Christmas, when it's not New Year. So what's the problem? Well, when CPU credits deplete, we see that on the instance, the database throttled to baseline CPU. So the query time increases significantly. It can be 5 times or even worse. But Progress doesn't know it's being throttled because it's at the CPU level. So slow queries will then hold the connection longer. So when having more uh, visitors coming into your apps or websites, the connection pool will be exhausted. But it can get even worse than this. So when the connection held longer, as we said just now, the connection pool saturates, and then more visitors coming in, then that is the time when you see, wow, P99 latency spikes and app layers times up. So this is when the PostgreSQL start to reject the connection. So at this point, maybe your grafana alert will start to send you alarm that saying you have a production outage. But it actually gets worse than that. It doesn't mean the Postgre just uh, start to reject, but the health check will fail. And then the orchestrator on Azure, for example, will start to restart the database. And because of this heavy restarting, it will burn the remaining CPU credit. So actually, you will go into the death spiral where it will keep on burning your excess CPU and you can't recover. So manual intervention will be required at this to break the loop. So this sounds very serious if you didn't know how the token bucket algorithm works. So there are a few solutions to this. So one is, of course, use over provision. You just don't use B-series entirely. And you just pay for the normal, like the general purpose instance. Well, it works. Actually, it's a very safe option. But when your business scale up, then it will be very expensive. You're actually overpaying. Second way is that you try to find out what are the configurations, what are the setup that you need, and then you do a load test. For example, you run Grafana K6 on it, and then you monitor over the time. But this is wasting a lot of time. If you need a week of data, you need to run your load test for that week. So that's why I would like to introduce you another way, which is called simulation. So we use more math to model the token bucket algorithm so that we can get good enough result in a very fast speed. So the simulation approach is like this. So in our demo today, we will use simulation to model the credit mechanics, the CPU credit mechanics, and then the queuing behavior. So simulation will act as a filter in our case. Okay. So just to clarify, what I mean is that simulation is a filter. It's not a total replacement for load tests. So it helps you to, let's say you have 100 configuration that you think your setup can be done, but you are not sure which one is the best. So simulation helps you to run all these 100 configuration and find out the best, for example, the best 3 instead of like best 100. Then you load test the final 3. Then you find out the best one. So this is the use case of our simulation here. So why are we using discrete event simulation, or we call DES? So DES models system by following each event step by step. So what do I mean by that? For example, imagine you're watching a movie. You are not interested in the heroes going to take a shower, having a dinner, or just sleeping for 10 hours. That doesn't add anything to the movie, right? What you are interested is the event, the fight, the key happenings. So discrete event simulation is the same. So it only models the event at each particular time, which is important to the simulation. So when we chain out this event, we form a list called the future event list. So if you are already aware, the token bucket algorithm that we showed just now are actually a graph of events. So when your CPU hit 0, it's one event. When your CPU recover, it's also an event. So in discrete event simulation, we have three things. We call it the generator, the queue, and the server. So generator in this case, in our demo, we will be using a distribution to random generate the visitor, to simulate the visitor incoming. And then the DB connection pool in this case will be the queue. Of course, the burstable instance that we model against is the server. So with these elements, we can actually model using discrete event simulation. So last year, I learned from my professor in National University of Singapore, Dr. Lee, and come up with my own open source library for discrete event simulation called SNA. It's done in C# and the latest .NET framework, which is .NET 10. Of course, the latest now is .NET 11. But yeah, the general purpose is .NET 10. So with this library, I'm able to model what we discussed just now with the MMCK So it provides deterministic logic for the stochastic inputs. And as you see just now, the table, right, with a lot of baselines and unrates. So I just put them in as the input parameter for the simulation. And then I can configure and then I see what is the output from the simulation. With that, I can validate against the queuing theory prediction. If you are interested, you can scan the QR code over here, which will lead you to the GitHub repo of my project. So back to our question earlier. So how do we know at what point our specific workload transition from bursting to the death spiral that we discussed earlier? We need to know like, so imagine now you don't have simulation. What you can do is that you set up this burstable instance with Postgres on Azure or AWS. Then you let it run. Then you do a load test on it. Then you monitor over a few days just to get the result. So how can we shorten this? And this is how we use the simulation. And in fact, I can get the result, which I will show next in just 1 minute. Actually less than that. So how do I do that is that, again, it's a similar graph, but this shows how I model the credit token bucket algorithm. So with the credit available starting point from the left, then the query starts. Then my code in SNA will check whether there's a sufficient CPU credit or not. And then if it doesn't have enough CPU, this will go to the baseline mode. But if you are still burn credit but at the baseline rate, then you slowly recover by earning the excessive credits. When you have enough CPU, then it will go to the burst mode with 100% CPU. That is when your database is able to perform at its highest rate. So it's the same graph, and we model it in C# code. So the result is this. So as you can see on the graph here, so the credit start is 60. If you still remember the table just now, before B2MS start at 60. Then it has a linear depletion as the burst usage exceed the earn rate in our demo here. So as you can see over time, after like about 20 minutes, the credit will hit 0. Yeah. and then it will stay at 0 forever because it can't recover. So from this graph alone, you will see your setup actually has this death spiral issue. So you can easily find out before you even set out on Azure through simulation. So what happens when the credit hit 0? We can also find out through simulation is that there's a 5 times degradation for the CPU bulk queries. So production cascading effects are getting worse. So this is why database is up. Sometimes doesn't mean the database is actually working. So at this point, I didn't even set up anything on my Azure yet. I just use mathematics to model the entire behavior through simulation. Another question that we commonly have is that, how big should my connection pool be? So some people have this idea of getting as big as possible or just increase the connection pool size when your database is slowing down. So, but is this assumption or is this behavior good? Can we do shift left testing on this kind of question as well? Well, the answer is of course yes. Otherwise, I won't put in the slide. So yeah, the discrete event simulation with my SNA library will be used in answering such questions. So as I shared just now, so common advice will be like just having pool size of 5 or 10 or 50 or 100. But they have some assumption which may not applicable to your use case. So 5 can be working for a startup database, but may not be working for your popular enterprise solutions. So how do we simulate this? So in this demo, we can use simulation to find the smallest pool within the 5% of optimal latency. Okay, so when I run the demo with the simulation code, what I get is this graph as you can see over here. So we have, I run the test for pool size of 5, 10, 20, 50, and 100. And it's surprisingly, after the 10 pool size of 10, actually the improvement is not a lot. So we found out that the optimal for steady load in our demo actually can be handled by a pool size of 10. So when you add more to the pool size, it actually doesn't help much to the latency. It will always stay after 55, 56 milliseconds. So this is the coolness of doing modeling and simulation to find out the results before you actually deploy. So you may ask, does this only happen for Azure? No. As I shared just now, Burstable instance is very common in all the cloud providers. In AWS, it is called the T-series. But across the different cloud providers, they have different minor difference among them. So for example, I actually did AWS modeling on this also. For AWS, the initial credits of the T-series always start with 0, unlike the Azure which is 60 or some non-zero numbers, depends on your size. And in AWS, there's this thing called the T-series. So it's called the unlimited mode. So unlimited mode in T-series means that instead of depleting your CPU, when you hit the 100%, when you burn out all your CPU credit, all your savings, it will still allow you to continue to run your database at 100% of CPU. But it will charge you more with the excess CPU. So this is the difference between different cloud providers. And of course, the baseline percentage is kind of different between different cloud providers. But anyway, the fundamental, the math, the principle will all stay the same because same approach works across all cloud providers as long as they are using the token bucket algorithm. So you may ask, is it overkill? Yeah. So last time when I shared this with AWS community, So they ask, are you overdoing something, which is we can get easily with guessing? Yes, of course, you can just guess like the pool size, connection pool size, or you can just guess when your CPU will hit 0 and so on. But that only works if you are working in a small team and a small infra where you can change your configuration very fast. If you work in an enterprise solution with like 50 or hundreds over instances, it is very dangerous and very costly to just use your assumptions to determine what is the connection pool size to use. And it is even more costly if you actually deploy this and you use load tester to run the load test to hit your production or UAT database, because that will actually be charged by the cloud providers. So over provisioning is never a small method for those enterprise solutions. So it depends. If you have a very small scale of database configuration, of course, you can just guess and you can trial and error to fix it. But for a large scale of enterprise simulation, modeling is always the best way that it can give you answer in a very fast manner. So what I shared just now is that we have seen how we model the CPU credits as well as the queuing. But I did not model the IOPS throttling, the network, and the storage latency. You can do so by checking out my code and adding more to make it more robust. But what I show you is only the CPU credit issues. One more thing. So when I was preparing for this presentation, I actually add one more very important things to our SNA library, which is called the observability. So with the OpenTelemetry integration, now when you run your simulation over different configuration, you can actually see the performance on your dashboard. For example, Grafana dashboard as shown over here. So yeah, you can see the performance cliff, and you can easily get your graph out on real time. Yeah. So the today's conclusion of this sharing is that instead of like guessing, we do performance testing on our infrastructure by shifting left using discrete event simulation. So before simulation, you just guess or you just test in the actual cloud environment. But now you can do it locally. You can run as many tests as you want, and you can identify the failure points before it happens on the cloud, which will cost you money. And instead of running it for days or weeks to just see the pattern, you can now narrow it to just a few seconds or 1 minute. And it gives you a data-driven results to help you better configure your infrastructure on the cloud. So yeah, thank you very much for your time attending to my talk today. I hope it's helpful because discrete event simulation is not something that you hear in the talks. It's a kind of academic, but I found it can be very useful in the real life production work as well. So if you would like to find out more, which actually I posted all my demos code on this repo, you can check it out. And you have more questions to me after this event, feel free to connect me on LinkedIn, and I'm happy to chat with you on this matter. Thank you very much.